So welcome and thank you very much for joining our session. My objective today is to lead us along a path to describe a simpler way of developing variable rate fertilizer applications for nitrogen. I'd like to start out by looking at the nutrient layers and how nitrogen is available and taken up by plants. Then introduce the concept of performance zones, which then leads us to a simple means of developing variable rate fertilization programs. So I'd like to start with looking at where nitrogen is available and how it's taken up by a plant during its growth phase. And this kind of plot is something that all farmers should be very well aware of, but for people who are not directly involved in farming, maybe this is something that you haven't come across before. But all plants start from a seed. They form roots at the bottom. They basically break out through the surface of the soil and form tillers. From there, the stem grows, it produces heads, the heads flower, and then eventually the seeds or the heads fill up with seeds and the seeds fill up with starch and protein. So this is the cycle for all cereal grains. And nitrogen is required at all stages of the development of the plant. Now, in the emergence and tillering stage, the nitrogen sets the yield potential. If there is not enough nitrogen available to the plant, then it may not form enough tillers. A healthy wheat plant should have 6 to 8 tillers, but if there's not enough nitrogen, it might abort some of those tillers and end up with 4. And that sets the yield potential. In other words, once the plant starts to grow, it can't go back and add more heads or stems. So the number of tillers, the number of therefore stems that grow, dictates what is the yield potential. 70% of the nitrogen that is taken up by the plant occurs in the stem and elongation and leaf production. In other words, it's producing the biomass. Nitrogen is used in photosynthesis to basically produce the sugars, which then go on to produce the seed. In the flowering and head development stage, there's another point at which the yield can be set. Plants are trying to reproduce themselves. So their objective is to make sure that there's enough seeds produced to propagate. So the plant will abort the heads or reduce the number of seeds on a head in the attempt to take whatever nitrogen or nutrients are available to ensure that there are seeds to then propagate in the future. Now, when the plant goes to its end process where it's actually filling the grain, if there is excess nitrogen, then that nitrogen will go to form more protein. Now, the relationship between yield potential and actual yield. Yield potential, as I said, is set by the number of tillers that turn into stems and then into heads. The yield is driven by how much water and how much nutrient, predominantly nitrogen, are available to basically drive the process to completion. The point is, you cannot recapture the yield once a tiller has been aborted, and you can't recover anything at the end by just adding more fertilizer. It's important that the plant has access to the nitrogen and the water at each stage of the growth. The actual yield is driven more by the number of heads and how they are filled. As I said before, if at the end of the process there is excess nitrogen, well, that's what goes to produce high protein grains. So if you've got fewer tillers, that sets the yield lower, and you've got excess nitrogen, you end up with low yield, high protein. I'd like to just put in perspective that that's a scenario that I'm going to point out later. So really, we can look at yield and protein as 2 measurement systems that can help define how the water and the nitrogen has been used. Yield predominantly looks at the plant development itself and how the water and the nutrients have been used. It's looking at the quantity, whereas measuring the protein shows whether there's been enough of the water and whether the nutrients have got to the seed, to the plant, so that you can actually produce the quality, which is the final seed to the protein. What we're saying is that for a long time, yield has been available, but not really been able to help farmers get a handle on how to add more fertilizer to increase the yield. But by combining protein and yield, then we believe that it's a much better picture, a more complete picture of how water and nitrogen can influence the crop's performance. Now, in terms of availability, well, within soil, nitrogen is available as a natural part of soil. It's from the breakdown, the organic matter breaking down, mineralizing, forming salts, in other words. It can also be fixed coming from legumes, a rotation crop. Application of a fertilizer. I actually put in another item here. Well, on the downside, or how it's lost, is the denitrification, in other words, the conversion of the nitrate ions into nitrous oxide and then released to the atmosphere as it diffuses through the soil. There is also leaching. When you get a rain event, nitrates can be washed to a lower layer beyond the root zone and therefore not allowing the plant to get access to it. And then lastly, you're going to lose nitrogen by the plant producing biomass and seeds. So the fertilization is the opportunity to increase or change the available nutrients, especially nitrogen, in the soil. There's been a puzzle in precision agriculture of where and how much nitrogen to add to the soil. That really is what we're talking about, variable rate fertilization. Yield maps have not been a very reliable method of developing variable rate fertilization prescriptions. Some years they work, and some years the data flips, and so you get the reverse situation. Satellite imagery, which has been available for the last 10 years, and more recently through drones and N sensors on tractors, really gives you a relative figure. It shows you and compares different parts of the field, but it doesn't really tell you about the amount of nitrogen that's being used. Whereas by measuring protein on a non-combine analyzer and combining it with yield, now you can start to get a much better picture of what the amount of nitrogen that was available and how it's been taken up by the plant. There's been quite a lot of research done over the years in several countries on the effect or the relationship between protein, nitrogen, and yield. Rowan Brill and Neil Fattel, two well-known agronomists in Australia, with Gardner and McMullen, basically produced a report in 2012 on some studies that they did at Trangie Research Station. What they had was 10 different varieties of wheats, and they in various plots, and they applied an extra 30 kilograms of nitrogen, urea nitrogen, in 30 kilogram steps. So they went 0, 30, 60, 90, 120 kilograms. And then they looked at the yield response and they looked at the protein response. What they found was that on average, the yield was maximized with a nitrogen application of 90 kilograms per hectare. And they also found that the yield appeared to maximize at a grain protein concentration of 11.2%. Now, if you look at the plot, you'll see that the mauve curve and the blue curve, they cross over at around about 120 of nitrogen application and around about 11.3 protein content. Really what this is saying is that as you add more fertilizer, you can increase both protein and yield, but at a point, the yield will flatten out. Adding more fertilizer is not going to increase the yield. the protein will increase, but at some point these two lines intersect, and where that intersects tells you pretty much where the optimum amount of fertilization has occurred. And that can then be used in the next season to predict or to allocate how much fertilizer I'm going to put into various zones. The same characteristic or plot was suggested by Steve LaRocque. Now, in this case, he's referring to barley. And what he's saying is that the balance, which he refers to as the sweet spot, is where the yield is optimized and the protein grade realized for highest crop payments. What he was looking at here is the fine balance between adding more fertilizer to increase yield, but if you increase the protein so that the barley gets downgraded or gets outside the malted grade, then you lose money based from the payment of malted grade barley. But look at the shape of the curve and where the two lines intersect. Now, different plants, wheat, barley, different varieties have different crossover points or optimum points, but they're all roughly about that 11 to 12%. And lastly, we see a study that was done in the UK. Professor Roger Sylvester Bradley reported in a report called Nitrogen for Winter Wheats Management Guidelines in 2009. Now, his plot is a little bit different, but if you look at his conclusion, it's basically the same. Grain protein with optimum N for yield in feed varieties is consistently about 11%. He says for other varieties it's 12%. So between this 11 and 12% is where the optimum yield is going to occur. Now, at first looking at this, it could be interpreted that, oh, we're putting the horse before the cart. Now, what you've got to understand here is that measuring the protein at when the yield has maximized or been optimized, that tells you, okay, that's the point I've got to try and get my protein to. If I want to reach an optimum yield, and yield is going to produce more income than the protein, then I should try and get my fertilization program such that I've optimized between 11 and 12%, definitely not 9% or 8%. That's where I'm going to be suboptimal. So it's increase the fertilizer content till I can get to that optimum. Beyond there, any extra fertilizer, all it's going to do is add extra protein. And yes, that could be beneficial in getting optimum, higher grade payments, but it's not going to increase the yield. So what are we looking at here? So what the experts have been saying is yield reaches a maximum at approximately 11.5% protein. If you add more nitrogen fertilizer, you can increase protein, but you're not necessarily going to increase yield. By measuring the protein and the yield and using that together as the basis for your fertilization program, you will better get a better understanding of how the water and the nitrogen has been available and uptaken, and therefore how it influences your crop. Now, I like to use this quote. Michael is a colleague of ours, but he's very much a well-respected soil scientist. The yield map correlates directly to soil performance, and the protein map is a very good proxy for plant performance. The nitrogen data is what makes everything else fit together, productivity and performance. Peter Drucker, well-respected business guru, one of his famous quotes is, if you can't measure it, you can't improve it. So how is nitrogen measured? First thing I want to establish here is the relationship or the link between nitrogen and protein. And we're talking about using near-infrared analysis in a combine to measure protein. Near-infrared measures protein, oil, and moisture in grains and oilseeds. But specifically for the protein, which in wheat and barley, it's between, say, 6 and 18%, but in soybeans where it's much higher, 30% plus, then all the proteins that make up are made up of amino acids, which then contain nitrogen and sulfur. And you can see in the graph there, lots of typical amino acids and all the nitrogen, hydrogen bonds that are there. And that's what the near-infrared measures. So nitrogen makes up 17.5% and sulfur 3.5% by weight of all protein molecules in wheat. Barley, it's 16.8. So if you want to convert or measure nitrogen, then you take the protein measurement multiplied by 0.175, and that will give you the percent nitrogen. If you multiply that by the yield, then that gives you the amount of nitrogen. And likewise with sulfur, you take the protein multiplied by 0.035, that gives you the percent sulfur. Now this can be quite well seen in this particular graph, a bit busy, but I'll just highlight these 2 points. You know, every ton of wheat that is stripped from the field, you're removing between 15 and 32 kilograms of nitrogen, depending on the protein content. So if you have a crop which is 4 ton per hectare yield, but 9% protein, then you're removing 63 kilograms of nitrogen from the soil. If you have a 4 ton crop, but at 14%, you're removing 98 kilograms. A 1.5 times, a 50% increase in the amount of nitrogen is removed from the soil dependent on the protein. So measuring the protein directly reflects the amount of nitrogen that is going to be removed from the soil. Now, measuring nitrogen from soil to stem to seed, we can start out in the soil. There are many means of measuring nitrogen and other nutrients in soil. The most accurate and reliable is to do core samples, take them to laboratory, and they will give you a full profile of all the elements and all the nutrients. Typically, the number of samples that are taken from a field is the big limitation, and also the cost. There are methods such as inductive electromagnetic induction, gamma radiation, which can give you a bulk density of the ions, the ionic effect of minerals in the soil. They don't measure the individual minerals. The correlation to nitrogen can be made in some cases, but it may be very poor in others, depending on what else is in the soil. This is done obviously before harvest. During harvest, we have NDVI imagery, and that can be done on a satellite drone or a tractor-mounted end sensor. And here we're looking at the effect of nutrients and water on producing the biomass and then the seeds. Now, the NDVI has become extremely popular, but it's a qualitative measurement. And then more recently, we have on-combine NIR analysis, which looks at the nitrogen, sulfur in the seeds. So soil testing, it's a direct method. The measurements are low density. It's been around for a long time and is very useful to understand how much nutrient is in the soil to start with. But the density, the low density, is probably the limitation and the cost. NDVI provides very high density information. It's an indirect measurement. It doesn't actually measure nitrogen. It measures green. The correlation to nitrogen can be very poor, and that can be because what the NDVI is looking at is the green of the biomass, and that can be affected by disease, by moisture, by soil type. And so you don't tend to get a very strong correlation. Overall, NDVI is more of a qualitative technique or method. Whereas an on-combine NIR analyzer is a direct measurement, as I've explained in the previous slides. The correlation to N is extremely high, 0.95 plus. The big thing is that it's a quantitative measurement. It actually gives you a number which you can then go back and say, this is the amount of nitrogen that has been removed from the soil, not just based on yield, but based on yield and protein. And therefore, that number can be used for real management to really control the amount of fertilizer that you're going to place in the field, with the end result to increase the yield, the quantity, and increase the quality of the protein. Now, these type of presentations should not be a sales plug, but I need to actually introduce the NIR Combaton on-combine analyzer. Now, this is a system that is mounted onto the combine. The objective is to take real-time measurements for protein, oil, moisture, starch in wheat, barley, rice, corn, canola, soybeans, oil seeds, in other words, and pulses, peas and beans. And there are some other crops that can be done. Originally, when we introduced this technology in 2013, we saw the real benefit for farmers to be in the area of blending based on protein. But now we find that it's the protein field mapping and the application or the development of variable rate fertilization, which is where the real return on investment comes from farmers. So the system, we have a sample head which is mounted to the clean grain elevator. As the grain passes up the bucket elevator, it falls into the top of the sensor head. A vein at the bottom of the sensor head traps the grain. Light passes through the sample, through the fiber optic and back to the sensor. When the spectra is taken, the bottom flap opens, the grain falls back into the downside of the clean grain elevator, and so that we're getting a reading about every 5 to 12 seconds, depending on how dense the crop is. Very dense crops fills the cell up almost immediately. Low density crops takes a little bit longer to fill up, and so that's the regulation of the time. Turning that into readings per hectare, about 88 readings per hectare, or about 9,000 in 100 hectares. So the information goes to the spectrometer, which sits in the cab. It produces the near-infrared spectra. The computer applies the calibrations for protein, moisture, and oil. It reads the GPS signal from the GPS transponder, which is mostly coming from the installed system in the combine. And then that presents the data in a number of different formats. We also have a proximity sensor mounted on the outloading auger. The objective there is that every time the outloading auger is extended, that tells the software that that is a full load or a full bin or a full tank. And since that's the minimum or the maximum amount of grain that you can actually blend, store, allocate, then that's what you've got. You've got 7 to 10 ton of grain. Okay, what is the running average for protein, moisture? Collect the weight from the yield monitor or take it from a Libra cart scale from Agromatics or a Digistar scale. Anything that basically will give you the weight of the grain that's been outloaded. And then that becomes the information for that particular tank. So there's a number of ways that the farmer can interact and look at the data. Probably the starting point is just a continuous stream of protein, moisture, and oil if you're doing canola. But it's the bin average that's probably the most important. Paddock average as well, but it's the bin average. Because as I said, that's the smallest parcel of grain that you can actually do something with. You can get real-time field maps for protein, moisture, and whatever constituents. And as you're going around the field, then this will propagate and it will show you those parts of the field where the protein is high and low. There are a number of graphs to show you what is the average or the bin figures for each load, or we can look at that as a table. And here we're actually allocating what silo or bin or chaser bin, where it's going, so that we can manage the data directly from the combine. And there is a logistics package which allows you to track what the protein, moisture, and weight is as the grain goes from the combine into a field bin, into a cart, into a mother bin, then into field silos, and then finally into a truck. And then when it's taken out of the field and put into storage, and it could be on-farm storage, could be in the form of a silo, a grain bag or a shed, or it's sent off to the local elevator or silo or customer. So we're keeping a complete record of where the grain has gone. And every time the grain is taken from one source and put into another source, then the running average for protein, moisture, oil, if it's there, and the weight is corrected. So then when you bring all this data back at the end of the season, you can tabulate exactly where it's been stored, what's the running average of protein, moisture, oil, where I've sold it to, what are the contracts, how much I've been paid for. It's a complete record of what you've harvested. So enough about the instrumentation, but it's important to realize that you cannot achieve what we're suggesting unless you have an analyzer on a combine. No good just having an analyzer in the shed. You need to be able to see where the variation in protein is across the field. And really, this is the thing that every single user, and we've sold over 300 of these instruments in the last 6 years, realizes first, is that there's a huge variation in protein across all fields. Now, these three fields, wheat, barley, and soybean, have been taken from North America and Australia. And that's been a comment from many people. Oh, yeah, you're fine for Australia where you've got variation, but no, we don't have variation in our country. Well, I'm here to tell you that you do. And until you actually measure it, and as Peter Drucker said, you can't measure it, you can't improve it. Well, every field we ever map out, the variation in protein is huge. Now, what we've done is to take the protein data, which we generate on the CropScan, then the yield data, which comes from the in-cabin yield monitor, and we overlay those and do a correlation within each area. And so what we're looking at is there a correlation of low-high, high-high, high yield, low protein, low yield, low protein? In other words, we want to look at where one is high, one is low, or both are high. And we map that out in what we call a protein yield correlation quadrant map. And you can see that on the right side. So you can see the strips in the middle of the green. That's the sweet spot. That's where you've got the optimum relationship. So if we look at that in a better way, so what we're trying to do is develop 4 performance zones: low yield, high protein, low yield, low protein, high yield, low protein, and high yield, high protein. And these are what we call the performance zones. This is what we call we refer to the protein yield correlation quadrant maps as a performance map, not so much of a mouth. The performance zones help to identify where the nutrients have been the limiting effect on the crop's performance. So if you have low yield, low protein, what that should be saying is that you've basically under-fertilized. You have left yield, quantity, and protein quality in the field. You could have increased your payments if you had added extra fertilizer in those areas. If you have low yield, high protein, well, the problem is not so simple. This is probably due to some form of moisture limitation. It could be that a rain event has washed away nutrients. It could be that the nutrients have not been accessible. It could be that the moisture, the rains didn't come at the right time. But the blue zone is where you've got to do some experimentation. You've got to do some investigation. Now the yellow zone, this is where the low-hanging fruit is. This is where you have achieved a moderate yield, maybe a high yield, but not the optimum yield. And that's indicated because you have a low protein. If your protein is not between 11 and 12, then you've left yield in the field. This is the first area where we suggest that you should start to apply higher rates of nitrogen, because that's where you're going to get the biggest return. And lastly, you have the sweet spot, the high yield, high protein. Another way to think about that sweet spot is this is the benchmark. What am I doing right in this section? Why is it producing, I'm getting the right yield, the right protein, which is the quality aspect, and then look back at the other zones and figure out, well, what am I doing wrong? So there is a strategy that revolves around these to try and optimize the yield first and then the quality. I'd like to present to you a couple of case studies. Chris and Protin Holland are a family farm, about 4,500 hectares in Young, New South Wales. Young is in the central wheat area. It's a very good growing area, gets reasonably good rainfall. But Chris and Protin are very forward-thinking farmers. Now, they bought the instrument, the CropScan 3000H in 2016, and the first year you map out the protein. You start to realize that there is variation. And in Chris and Protin's case, they started to say, well, look at this, we're losing money. Now, in Australia, you grade wheat based on protein content. And the grades basically below 11.5 and below 10.5, that's the bottom grades. And you're not getting the full price. If you can get up to the 11.5 to 12.5, and then 12.5 to 13.5 or beyond, that's when you get the extra $20, $30 a ton. So then they took the yield map off their combine. They did the performance map or the protein yield correlation map. And then from there, they've got the high, low protein yield zones. Now, that led them to develop a simple urea application for 2017. And what they basically said is, well, where we have had low protein, we'll put in more nitrogen. Where we've basically got it pretty much right, the green zones, well, we'll really just take it away a little bit because we don't need to produce extra protein. We need to get the yield optimized. And in the other zones, we'll add a little bit more. Basically, we'll keep going in that area. The result in 2017 was now we see that the protein map, we have a great big area of green. And that green is where they've achieved H1, which is the premium grade. They get an extra $30 to $50 a ton more for it. But they've also got a whole lot more of the H2, but very little of the APW or the ASW. More importantly, they calculated that the yield across their field was balanced out. In other words, was a lot closer right across the field by as much as 40%. The net gain that they got through incremental price increases based on grade plus the yield was $14,850 or $81 a hectare for this field. This represents about 7% of their total crop. So multiply 81 or 14,000 by even 5, you can see the return that they would have got. The next case study is looking at it from a different point of view. It's looking about optimization of the fertilizer or reduction of fertilizer. And this was based on Leeton Ryan in Menangatang. It's a bit bigger farmer, I think he's about 7,000 to 8,000 hectares. And we've, Michael Ayres and Ed Scott have done a lot of work on his property, and we've worked with him as well. So here we see elevation map, protein map, yield map for 17. Then we see the protein yield correlation or the performance map. And finally, that is translated into a urea application. If you note that they've adopted a similar strategy, 3 zones, 80 kilograms, 60 kilograms, or 40 kilograms, based on whether in the correlation map it is yellow, red, blue, or green. Now what they looked at is their normal practice was just to do a blanket rate. So if they had used 60 kilograms per hectare across this field, 296 hectares, at a cost of urea of $450, then the total cost would have been pretty close to $8,000. But using the strategy that came from the performance maps and therefore developing the performance zones, they were able to distribute that fertilizer much better, and the total cost of fertilizer reduced by $1,260. And $1,260 may not seem like a great deal of money, but put into perspective of a percentage. Leeton's annual fertilizer or nitrogen fertilizer bill is probably in the $300,000 range. So if he can save 16% of that, then he's looking at around about $50,000 in cost reduction. Considering the instrument costs half of that, that's pretty good return on investment. So all decisions by farmers are going to be made based on return on investment. We're talking about how to implement variable rate fertilization strategies. So in year one, all you can do is measure the protein and yield, but you're going to get some benefit in blending. Nearly all farmers in their first year realize that I can increase my payment for crops $10 to $40, as I've shown in the previous slides, per hectare, based on just the fact that I can blend low protein with higher protein and jump a grain. If I jump from ASW to APW even, I can pick up an extra $10 to $20 a ton. One of the sidelines of the technology is it's a very accurate moisture measurement, much better than capacitance measurements. And that means you can start earlier with confidence that you're actually stripping grain at the right moisture, not due to just a dew effect, which the capacitance meters go crazy with. And then later at night, you can continue going on because you've got confidence. But you can also blend based on moisture to basically distribute the stuff that may be a little bit higher moisture at the beginning of the day or at the end of the day. Now, overall, that saves you time. And typically you can save maybe a few days, maybe even a week off your harvest. And that's where the percentage increase comes from. Some people have forward contracts. So if you use the technology at the first stage, just to strip those high protein zones to make sure that you're going to meet your contracts and therefore capture that extra $20, $50 a hectare, whatever the premium that you're being paid. So you get your agronomist or you get us to generate the protein yield correlation maps, and that leads you to year two. In year two, you apply these simple variable rate fertilizations. And first thing you want to look at is the yellow zone with a low hanging fruit. And from that, you should be able to pick up $40, $60 a hectare. As the years go on, 3 to 5, you're going to then start to look at, well, can I increase, can I drive a little bit harder in those zones? Can I address the red zone, which is the next one to look at? And finally, can I do something? Can I do some soil pits? Can I get an agronomist in or a soil specialist to figure out what's going on here? Maybe I have to deep rip. Maybe I have to change the nature of that soil. Overall, in a 5-year period, our objective is to get somewhere in the order of a 30% increase in productivity and profitability on farm. So what's our strategy? Simple variable rate fertilization strategies was based on yield and protein. It gives you a clear indication of the grain quantity and the quality. By combining the yield, the quantity, protein, the quality, you can define the performance zones. The performance zones are what you can then use to work out what is the drivers behind the water and the nitrogen. The nitrogen management is the easiest piece of the puzzle to action. In other words, you can try other nutrients, and we're not saying other nutrients don't influence plant growth, but nitrogen is the one that you're going to get the easiest and the biggest response from. So try that first. The protein maps, these performance maps, give you a clear indication where the nitrogen didn't keep up with the yield. In other words, if you use the nitrogen, the protein measurement as an indicator of where I haven't reached my yield potential, then that gives you the first place to look at. I'd like to finish up with just a couple of quotes. Steve LaRocque is a syndicated agronomist. He has a publication or a newsletter called Beyond Agronomy, and Steve is one of our users. And when he first got the system, after the first season, he came up and said, the ability to map protein and combine it with yield mapping is where the magic happens. This technology would make it much easier to blend grain when you know what you have. It can also be used to segregate based on moisture and protein. And lastly, I like this quote from Chris Holland. We're sitting in their kitchen, having a cup of coffee, talking about what to do next year. And Chris just said, 20 years of yield maps, but how can I use them? Then the last 2 years of protein maps, and it all makes sense. So our final message is we're trying to provide a means of optimizing yield in the field. If you'd like to find out more, please visit our website, www.cropscanag.com, or get in contact with us by Twitter, by email. But thank you very much for listening. And if there's any questions, we'd be only too pleased to field them.